Vasilis is going to give the talk.
So, hello everyone. This is joint work with my advisor, Christos Tzamos, and Manolis Zampetakis from MIT. So, a standard problem in statistics is that we want to estimate the mean of a population. So we see samples and we want to find the mean. So in our setting, instead of seeing samples from the whole population, we only see samples that fall in some specific subset of the space. So we only see these red points here. And the question is the same. We would like to estimate the mean of the underlying population, so the blue points. So I want to start with a fun story that I read on Gil Kalai's blog. So this is a fictional story, but I think it illustrates the problem nicely. So Poincaré, the famous mathematician, was going to a bakery where it was advertised that the loaves were 1 kilogram in weight. But Poincaré was suspicious, so he weighted the loaves that he bought. And he found out that their weight was a normal distribution with mean 950 grams. So he went to the baker and complained that he's stealing from his customers. So the mean should be 1 kilogram. So the baker responded that this was by mistake and that he's going to fix this from now on. So the next year, Poincaré continued to buy bread loaves from this bakery, and all the loaves that he got were above 1 kilogram in weight. So everything looked fine, but he went again to the baker and complained, and he told him, look, you're still stealing from your customers. The average weight is still 950 grams. And he was actually correct. So what happened? So what happened is that the baker was keeping the heavy loaves, so every loaf that was above 1 kilogram, and he was giving these loaves to Poincaré, and he was selling all the other loaves to the other customers. So what Poincaré observed was the upper tail, this red part here, of a normal distribution. So he was smart and figured out the part of the curve that was missing, and he figured out that the average weight was still 950 grams. So this is exactly the problem that we want to solve. Poincaré observed truncated samples that, from the upper tail, and was able to recover the true mean of the population. So let's now make the problem a bit more concrete. So we're given samples from this truncated normal density. So this is basically the conditional density on the truncation set. So this is the indicator function of the truncation set. This is the density with the normal density with parameters mu and sigma. And this here is the Gaussian mass of the set. So this is a normalizing constant, so that the whole thing integrates to 1. So the assumption that we're making in this work is that this normalizing constant, the Gaussian mass of the set, is lower bounded by some absolute value, 1%. So the problem now is, given data that are drawn from this truncated normal density, we want to find estimates of the parameters such that the untruncated distributions are close in total variation distance. So this is roughly equivalent to saying that we find it's parameter estimation of mu and sigma. So this problem has a long history in statistics that goes back to Galton and Pearson. And even though there are many results and books about truncated statistics, all these works consider simple truncation sets. So for univariate data, it's left truncation or right truncation or interval. And for higher dimensions, it's rectangles or boxes. So the first general result that dealt with complicated truncation sets is from Daskalakis, Gouleakis, Tzamos, and Zampetakis in Fox 2018, where they assume that the set S is known. So they have a membership oracle to the set. So for each point of the space, you can ask in or out. So given this oracle, they prove that roughly d squared over epsilon squared samples, with that many samples, we can learn the parameters. So this is a very nice result because this amount of samples is necessary when there is no truncation at all. So to learn a normal distribution, you need d squared over epsilon squared samples. And they prove that the same number of samples is sufficient when there is arbitrary truncation, as long as we have this membership oracle to the set. So the main open problem now is what we do when the set S is unknown, when the truncation set is not given to us in any way. So they construct a very complicated truncation set that makes it information theoretically impossible to recover the mean. So now, this is not the end of the story, right? We have We have, on the one hand, we have the simple truncation sets of the older works in statistics, like boxes and rectangles. And we have this super complicated truncation set that makes it theoretically impossible to recover the parameters. But the real question is whether we can do something in between. So if the truncation set is unknown and has bounded complexity of some sense, can we still recover the mean of the normal? So that's the topic of this talk. So this is a picture of the data that you get. So these are data points from a two-dimensional Gaussian distribution. So originally, this should look like a disk. But it was truncated in this strange triangular thing. And this is what you get now. So the conditional mean, the mean of this data, it should be somewhere in the middle. But the mean that generated the data points, so the Gaussian distribution that generated these data points, has mean 0, 0. And now this data set corresponds to a very different Gaussian, although it looks the same. So the Gaussian that generated this data set has mean that it's over there. So the question is whether we can distinguish between these two cases. So our first result is an information theoretic result. So we prove that if the family of the truncation sets is of bounded VC dimension, then with d squared over epsilon squared plus an overhead that depends on the VC dimension, we can recover parameters such that the total variation of the untruncated distributions is at most epsilon. And we prove that this dependency on the VC dimension is actually unavoidable. So we construct a family that has VC dimension, a family of truncation sets that has VC dimension roughly 2 to the d, and getting a constant approximation to the mean requires roughly 2 to the d over 2 samples. So let's see now how this result roughly works. So a natural question is whether we can first learn the set, learn the truncation set, and maybe run the previous result with the membership oracle, right? This sounds like a reasonable approach. But this is not possible, or it's not easy at least. So the task of learning a good truncation set is coupled with finding the parameters of the normal distribution. So just finding a set that contains all the samples is not enough. So let's consider an example. So here you have univariate data, and the family of truncation sets is just thresholds. So it's either left truncated or right truncated. So you're looking for either a lower or an upper bound. So if you knew that the Gaussian is on the left, so if you knew that the Gaussian is this blue point here, you would pick the left truncation. Because if there is no such lower bound here, you would have observed some data points here, right? So similarly, if you knew that the Gaussian is on the right of the data points, you would pick the upper bound for the same reason. So finding the good truncation set depends on the parameters of the Gaussian. So even though it's not clear how we can find the good truncation set, we can find a tuple. So we can find mu tilde, sigma tilde, and the truncation set, such that the total variation distance between the truncated distributions is at most epsilon. So we match the truncated distribution. And at this point, it's not clear whether this translates to the untruncated distributions being close. And this is the main technical result of this part. So we prove that this is actually enough. So if you manage to match the truncated distributions in total variation, then the same parameters will also result in the untruncated distributions to be close in total variation distance. So far so good. The problem of this result is that it doesn't give us a unified approach that works for all low complexity sets. So we have to do something similar to an ERM procedure for this result. So we want to find a set that contains all the samples. So if you knew that your family of truncation sets is ellipsoids or rectangles, you have to implement something different each time. We would like to have a generic approach that works for all low complexity sets. So to this end, we're going to work with the Gaussian surface area of the set. So this is basically the surface area, but with respect to the Gaussian measure. So this set on the left is a complicated set with large surface area, and this is a nice, simple set with small surface area, or perimeter in this case. So this is a hard set to learn, this is an easy set to learn. And the assumption that we're going to make is that the Gaussian surface area is at most some constant gamma. Okay? So our first result using Gaussian surface area is an information theoretic result we proved that if two truncated normals have kappa matching moments, where kappa is gamma squared over epsilon to the 8, then there are also closed nodal variation distance. And the main result now is an efficient algorithm. So we proved that with roughly d to the kappa samples, where kappa is this, Gaussian surface area squared over epsilon to the 8, and in polynomial time in the number of samples, we can find an epsilon approximation to the mean. So in this statement, we assume that the covariance matrix of the Gaussian is identity. We generalize this to work for diagonal covariance matrices, and we don't know how to solve the general covariance matrix case. So we also prove that this result is almost tight. So we construct a family that has Gaussian surface area roughly d, and again, getting a constant approximation of the mean requires roughly 2 to the d over 2 samples. So to get a rough idea of how large this Gaussian surface area is, let's see some popular concept classes. So degree k polynomial threshold functions have Gaussian surface area k, so we need d to the k squared samples. D is the dimension. Intersection of k-half spaces have square root of log k, and general convex sets have d to the 1/4. So the Vc dimension of general convexes is unbounded, but the Gaussian surface area is bounded. So this means that these, the convex sets are learnable when the distribution is Gaussian. So the main ingredients of our approach is polynomial approximation and stochastic gradient descent. So let's see now how our algorithm roughly works. So we're going to use the Hermite polynomials. Here you can see the first 3 Hermite polynomials. And this is basically an orthonormal basis with respect to the standard Gaussian distribution, so N0. And what we like about these polynomials is that we can approximate functions with them. So the ideas here are exactly the same as the standard Fourier basis with the sines and the cosines. So if you want to approximate a function with a finite sum, you basically project the function to the subspace that is spanned of all the Hermite polynomials of degree at most kappa. So you write this as this linear combination, and the coefficients of these linear combinations are the inner product of the Hermite polynomial of degree v times the function. So this is the inner product with respect to the Gaussian density. So here, for example, we want to approximate the step function, and the blue curve corresponds to the approximation of degree 5, and the orange curve corresponds to the approximation of degree 40. So the higher the degree, the better the approximation becomes. So let's see now how we can use these Hermite polynomials to solve our problem. So we want to find the Hermite coefficients of some function. This is the plan. And since we have samples from this truncated density, let's see what happens if we evaluate the Hermite polynomials on these samples. So we draw a bunch of samples from the truncated density, and then we evaluate the Hermite polynomial of degree v on the samples and form this empirical Hermite coefficient. So let's say we draw an infinite number of samples. So let's try to find the expectation of this empirical coefficient. So this is an expectation with respect to the truncated density. So we can rewrite this as an expectation with respect to the standard normal. Here is the Hermite polynomial, and this is just the truncated normal density. So now remember that the formula for Hermite coefficients is this one. So it's the inner product of the Hermite polynomial of degree v times the function f that we want to approximate. So basically, what we have here is that when we evaluate the Hermite polynomials on the samples, we recover the Hermite coefficients of this red function psi of x here. Okay? So this is a very nice function because it's basically a weighted indicator function. It's this indicator of the set S times an exponential factor here. So this has enough information to recover mu. But the first question is how large this degree of the polynomial should be so that we get good approximation to this weighted indicator function. So in a previous result, Clevans, O'Donnell, and Servadio proved that with degree kappa, roughly gamma squared over epsilon squared, we can find a good approximation, a good polynomial that approximates the indicator of the set. So we extend this result, and we prove that with slightly worse degree, gamma squared over epsilon to the 4th, we can find a good approximation to this weighted indicator function, psi of x. And the number of samples that we need to get this approximation is roughly d to the kappa. Okay, so this is where the sample complexity comes from. So this is a picture of, this is an example of this weighted indicator. So this psi of x is 0, it's just a threshold, it's 0 before 0, and then you have this exponential thing. And what we learn is the blue curve, okay? So the blue curve is the degree 30 polynomial to this function. So now, let's see how we can use this function that we learned to recover the mean. So the goal is to formulate an objective and run SGD. So this is what the objective should look like. So we draw samples from this truncated normal density, and we want to find an objective that looks like this. So we cook up, I don't want to get into details, but we cook up a correction function h such that when you multiply it by psi of x, this objective is convex, and the minimizer of the objective is the true parameter of the true mean of the distribution. So unfortunately, we don't have psi, we have our polynomial approximation. So this is our objective now. And a main technical result is that if the degree of our polynomial approximation is high enough, so if it's gamma squared over epsilon to the 8, then the minimizer of this approximate objective function is epsilon close to the true mean of the Gaussian distribution. So to be able to run stochastic gradient descent, we also prove that this objective function is actually strongly convex, and the variance of each step is bounded. So this is the whole algorithm. We formulate this approximate objective function, and then we run stochastic gradient descent from the samples of the truncated normal distribution. So I would like now to conclude with a summary of the results and some open problems. So in this work, we give nearly tight sample complexity results with respect to both VC dimension and Gaussian surface area. And we give the first efficient algorithm that works for truncated statistics with unknown truncation sets. So now, some open problems are whether we can extend these results beyond the Gaussian distribution. And actually has been some recent work that deals with the case of mixtures of Gaussians, truncated mixtures of Gaussian distributions. Then another nice problem is whether we can improve the runtime for specific classes. So in this work, as I said, we find a unified approach that works for all low complexity truncation sets. So maybe if you knew that your truncation set is an ellipsoid or a rectangle, maybe you can do much better. And finally, maybe a challenging open problem is to make the sample complexity depend polynomially on the accuracy parameter epsilon. Because in our result, we have this accuracy epsilon at the exponent. So we have d to the gamma squared over epsilon to the 8. So it would be very nice if we could get this to be polynomial in the accuracy epsilon. Thank you.
Okay. So the information theoretic result, does it require the amount of Gaussian mass you retain in the set, this alpha, to be at least like inverse polynomial or something? Like.
Right.
Oh, that
yes.
also requires. Okay.
Yes.
So you know it's information theoretically impossible if there was only an exponential fraction of mass. Do you know like?
No, it won't be information theoretically impossible, but the number of moments that you need to match depends on this alpha. So it will be an exponential. It will be.
I don't know. I mean, like in maybe some other method, not necessarily moment matching. Would it? I'm just curious. Like if there was only 2 to the minus n over 10 of the mass was retained by some set, is it information theoretically impossible to figure out?